So how about a real challenge, Professor Peoples? How about that? What happens if we're given a question like this one where we're asked to use implicit differentiation to find dy dx? So, if you remember implicit differentiation, this was the method whereby we would take the derivative with respect to x of each term, regardless of whether it had the variable x or y in the term, and then try and find its derivative using our derivative rules. And if you call, by the way, if we take the derivative with respect to x by the chain rule of, let's say, y, we know that that is really the same thing as just saying dy dx. Right? So we kind of keep in mind that we have this situation where we can get this y value in our derivative here pretty simply. So let's take the derivative with respect to x on both sides. So take the derivative with respect to x of each term on the left-hand side, right? So the derivative with respect to x of x times e to the 2y plus 4 times x minus 5 times y equals the derivative with respect to x of 3, right? Notice that we're just taking the same mathematical operation on both sides of the equation to balance it out. Now it's going to be a little bit hairy here because we're going to have to, well, take the derivative of each term individually, right? So we take, by the sum and difference rule, the derivative with respect to x of the quantity x times e to the 2y plus the derivative with respect to x of 4x plus the derivative, that's a minus, right? Is what I get with a leaky pen. Try that here, just correct that here so I can see it. All right, minus the derivative with respect to x of 5y. And we know on the right, if we take the derivative of a constant, we just get 0. So using our rules right here, this is going to be a product rule, right? We've got x times e to the 2x plus y. So in the product rule, we take the derivative of the first function, so the derivative with respect to x of x, times e to the 2y, and we're going to add that to x times the derivative with respect to x of e to the 2y. That should be a 2y here as well. All right, that's by our product rule. Now, in the next term, by the way, we're going to have plus the derivative of 4x. We know that's just going to be 4 times 1. Minus the derivative of 5y, and that's going to be 5 times the derivative of y, which we stated up here, must be 5 times dy dx equals 0. All right, well, let's work this one through a little bit more right here. The derivative with respect to x of x is 1. So we've got e raised to the 2y power plus, okay, we're going to have x times the derivative of e to the 2y by our exponential form of the chain rule is going to be e to the 2y times the derivative of 2y. Again, plus 4 minus 5 times dy dx. Then we take our derivative here of 2y. We know that's going to be 2 times, so we're going to have e to the 2y added to. The derivative of the 2y is 2 times dy dx, so it's going to be 2x times e to the 2y. I'm just taking that constant of 2 out, times dy dx, plus 4 minus 5 times dy dx. And now our next job is going to be isolate all of the terms that have dy dx on one side, all of the terms that do not have dy dx on the other. So I'm going to move this term right here and this term right here by addition to the other side of the equation so that I have the equality e to the 2y plus 4 is going to be equal to 2x times e to the 2y minus 2x e to the 2y by subtraction plus 5, and that's times dy dx. Now, I'm the kind of guy who likes having my positive terms in front and my negative terms in back, but in either case, I would just simply divide by this quantity, 5 minus 2x e to the 2y, and divide that on both sides. So my resulting expression for my derivative will be e to the 2y plus 4 divided by 5 minus 2x e raised to the 2y, which is equal to dy dx. And that's exactly what I was looking for, and so I'm done with this problem.